Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to cover the 2016 final, question 2. So, as you guys have seen in the practice finals, question 2 is always the same. It's going to be your bending moment, and shear force diagrams. I just about said bending shear diagrams, but that makes no sense at all. So, as expected, they're going to give you some sort of beam, and it's going to be simply supported, meaning you can solve it with your regular equilibrium conditions. And the question's basically going to ask you for the free body diagram, the shear force diagram, and then the bending moment diagram. So if we look at this question right here, it says, for the beam with the loading shown in figure 1, so we see that the loading is shown in, figure 2, I guess. There's a mistake on this final. It says 3 things for the first 3 questions. 1 is draw the free body diagram of the beam. And then it says determine the support reaction. So the beam is supported by this. Provide the magnitude and direction of each support reaction. So basically the first part's just draw the free body diagram and determine the support conditions. So that one's not bad. Second question says using the axis provided. So there's actually an axis provided, but I'm going to draw my own because I don't want to copy and paste it into here. It says draw the shear force diagram for the entire length of the beam. And of course, label all important shear force values and their locations. So we're just going to include the values of all the shear forces, and that's very, very standard. And then finally for part C, it says draw the bending moment diagram. So this is expected. Question 2, when we deal with beams, we're always looking at the shear force diagram as well as the bending moment diagram. But in order to solve those, we'll of course need the support reactions, which is in part A. So this question is kind of nice because they kind of hold your hand and take you through exactly what they want. So we're going to come down here and we're going to say part A. And the first part is determining those support reactions. And when we determine support reactions, we must always draw a free body diagram. Always. So I'm going to draw just a simple beam like this, coming up, coming across. And that didn't work. I need to draw a rectangle. All right, let's try again. So it doesn't look like a rectangle at all, but Notability helps me out and I'm good to go. So we're gonna start by putting on all the external forces onto the beam. So we see that we have a vertical load over here. We see that there's a concentrated moment, let's say somewhere right here. And then at the very end of the beam, we have a distributed load. So I'm not sure exactly where I want to put this. We'll just put it like this. So what I do for a distributed load in a free body diagram is I just draw the silhouette. And that one looks kind of crooked, so I'm going to get rid of this. Try to make it a little bit more straight. Again, we're not going to judge you if it's a little crooked. It's still a little crooked, but it doesn't matter. You guys won't judge me. We won't judge you. All right, so, and I replace it with a external force right in the middle. But this leads me to something very important I want to talk about. Actually, I'll finish the other forces and complete the free body diagram, and then we'll discuss it. But it's actually something very interesting that I have had a couple of students come and talk to me about, and that's drawing free body diagrams, blah, 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 blah. So we're going to put this one over here, and then on the other side we have a roller, so just a single force over here like this, and then we're going to label everything. So the point load, 15 kilonewtons. The concentrated load is 20 kilonewtons per meter, or kilonewton meters. The distributed load is 10 kilonewtons per meter. And of course we have our support reactions. So on the other side we got it at B. So I'm going to put BY. And on this side it's at point A. So I'm going to have AX and AY. Like this. And then the point for the distributed load I'm just going to call F1 for right now. Another thing we have to include in our free body diagram is, of course, dimensions. We have to say how far things are. So we got here to here, and then to here, here, and here. So we got 2 meters, 1 meter, 1 meter, and then 2 meters to finish it all off. So now this is one of the things I get asked. So for this free body diagram, it's good to go. It has all my external forces. It has all my reaction forces. And to finish it off, it has the dimensions of the beam. Now, one thing I got asked about a lot is this right here. This vertical force for F1. And I include this when I'm solving for support reactions. So the question I got asked is, when do I turn the distributed load into a single force? And the only time you do that is when you're solving for forces at a point. So if we're solving for reaction forces such as AY, well, we're going to replace that with a force. If we're solving for the internal forces at a single point, then we do that with the force. However, when we're drawing the bending, I was going to say bending and shear moment, but again, it makes no sense. The shear and bending moment diagram, we don't replace it with a point if we're just using our relationships. So if I was to just go right into this shear and bending moment diagram, I wouldn't have an F1. I just want to find the slope, which is 10. Oops, went to eraser, meant to keep it on highlighter. If I'm just drawing the shear and bending moment diagrams, the only thing I'm interested in is the 10 kilonewtons per meter, because that's going to be the slope. So I'm going to get rid of some of this highlighter now, because we're going to continue on. So remember, we have 3 unknowns. We have 3 equilibrium equations. And the first equilibrium equation is going to be sum of the forces in X is equal to 0. And this one's really easy because the only thing we have here is AX. So AX must be 0 kilonewtons. So that's one of the answers because it said provide the support reaction. So I'm going to box it in. It's nice to box all your answers. So we're good to go. Now, if we were to do sum of the forces in Y, what we'll quickly find is that we have 2 unknowns. We have AY and BY, so that won't really get us anywhere. So the next thing I like to do is we're going to take a moment. We're going to go sum of the moments, and I take it about the pin. So point A is equal to 0. So I take it about the pin, but you guys can take it wherever you want, as long as you guys can get one of the reactions. So when I say wherever you want, I mean at A or at B. Don't take it somewhere else because you can have the same scenario as sum of the forces in Y, which is you have 2 unknowns in your equation, can't solve for anything. So what I'm going to do is I'm just going to go from left to right in the beam and write down all my forces and find their moment arms, stuff like that. So the first one that I see from A is we got 15 kilonewtons, and we know that this point force of 15 kilonewtons acts at a distance of 2 meters from A. And the next thing we have to look at, of course, is what kind of moment does this create? And we see that this creates a clockwise moment, so this is going to be a negative moment. And then moving on, we got a concentrated moment of 20 kilonewton meters, and it's also clockwise. So we're going to have minus because it's clockwise, and then just 20. And finally, we have the distributed load F1. So we see that F1 is also clockwise, so it's going to be negative. And then we need to find the value of F1. So just down here real quick, I'm going to go F1 is equal to, and all it is going to be the area of that distributed load. So we know it's going to be 10 kilonewtons per meter, and that's the height of it, multiplied by the length, which is 2. So we know that F1 is equal to 20 kilonewtons. And we're going to put that up in here, so minus 20. And we know that F1 acts at a distance of 4 meters. So I'm going to show you guys exactly where I'm getting this from. So it's 4 meters to get from here to here. This is 4 meters. And then F1 acts at a distance halfway in the distributed load. So it's going to act right here, and then it's going to be 1/2 of 2 meters, which is 1 meter. So we know that for here, the moment arm for F1 is going to be 5 meters. So I'm going to go 5 right here. And then to finish it off at the end of the beam, we have BY creating a counterclockwise moment. So it's going to be plus BY, and it's 6 meters away from A. So of course, all this is equal to 0. And then in the end, we can solve, and we get that BY is going to be equal to 25 kilonewtons. And it was a positive answer. So our assumed direction that BY is up is correct. So I'm going to put 25 kilonewtons, and I'm going to put a little arrow like this saying that it is upwards. And it being an answer, I'm going to box it as well. So finally, we can come down here and end with sum of the forces in Y is equal to 0. So our last equilibrium equation. And it's not too bad because we're just going to go left or right. So we got AY at the very left-hand side. And we don't know AY yet, so we're going to just have AY. And going across, well, we got 15 kilonewtons going downwards. So minus 15. And if we keep going across, the next one that we run into is F1. And we see that F1 is 20 kilonewtons. So minus 20. And finally, at the very end of the beam, we got BY going upwards. But we know that BY is 25 kilonewtons. So we're just going to go plus 25. So this 25, well, that's just BY. And of course, everything is equal to 0. Our only unknown in this equation is AY. So we can solve, and we get AY is equal to 10 kilonewtons upwards, like this. Perfect. So what I'm going to do is I'm just going to highlight it because it's a final answer, or box it, highlight it, one of the two. As long as you make it very clear that that's your answer, you're good to go. So I see that I have my free body diagram here, and I have my three support reactions. So I'm good to go at this point. If we look at part A, we're good to go. And it's already 2 marks out of 10, so we're going pretty fast. I did this really slow, but I know you guys can probably do this in 1 or 2 minutes now. You guys are experts at finding these support conditions. So we're going to come down, and we're going to go to part B. And part B is a fun one. So again, they're going to typically, well, actually, I'm not sure this year. I wonder if this year they're going to give you one of those examination booklets that you got in the midterm, those loose leaf, really crappy examination booklets. I know I really hate them, but they might give them to you guys. So if that's the case, you guys will have to make your own axis. But as you guys see, making an axis is not that hard. You just got to draw 2 lines with a ruler. You guys will be fine. But when I'm doing this and I'm creating my own axis, what I like to do, because this will help me a lot for my shear and bending moment diagram. So actually at the top here, I'm going to go B and C, because I like to create them right underneath each other because they're so closely related. So I'm going to come down here, and I'm going to start drawing my axis. So my axis is going to go like this. And I'm going to have, let's say, shear start right here and come across. And we'll come down here, and I'll make this a little bit longer, but we'll have moment coming. Oops. We'll have the moment coming over here, right here. So just like this. And then what we should do is we need to draw our beam. So I'm going to draw the beam up here. And we know that the beam is 1, 2, 3, 4, 5, 6 meters long. We should probably double it just so it's not too bad. So we're going to say that the beam is this long. So I just doubled the scale. Again, scale doesn't matter too much, so don't worry about too much about the scale. We all know you guys are an artist. We're not expecting any sort of artistic things from you. Oh, yeah, so don't worry about it too much. So this is going to be our shear. And I won't get to moment yet because we're going to get to moment when we get to moment. So this is going to be 0, and this is going to be our shear in kilonewtons. And I'll show you guys exactly what I was talking about with the free body diagrams I was discussing above. So this black line all by itself right now, that's going to be my beam. And I'm going to draw all my forces on it so that there's no unknowns. So looking at this beam, at the very left side, we got AY, but we now know that AY is actually just 10 kilonewtons upwards. So I'm just going to put an upwards arrow, and I'm going to put 10 kilonewtons. And then I know at 2 meters across, we have 15 kilonewtons coming down like this. So right here, I'm going to put 15 kilonewtons. 2 more meters, we have that concentrated moment like this. And this moment is 20 kilonewton meters. And then finally, near the end of the beam, we have a distributed load that comes across nicely across the beam like this. And this one is when I'm talking about I don't care about where F1 is or what F1 is. Because when I'm creating these diagrams, the only thing that I'm going to be interested in is the slope. And the slope here is going to be 10 kilonewtons per meter, and I'm going to put that in. Or I guess not, you could say the slope or the magnitude. So I'm going to put 10 kilonewton per meter. So that's what I'm interested in. I'm not going to replace it with the force that called F1 or anything like that. So I'm just going to leave it like this. And I'm going to dimension it all so you guys all see where all the dimensions come from. So the first one, we got 2 meters, then 1 meter, 1 meter, and then 2 meters. So we're going to put 2 meters, 1 meter, 1 meter, and then 2 meters. And then now, with this all done, I can begin drawing my shear. So for shear, it's actually really, really nice because all we're going to do is just follow the loads. If we have a concentrated load, well, we're going to do a jump in our diagram based on the level of the concentrated load or the magnitude. And if we have a distributed load, we know that we have to use specific equations to find out what happens to our shear. So we're going to go across shear, and we'll draw it in this blue color. And for shear diagrams, we just want to go left to right. That's it. We're going to go left to right, nothing crazy, nice and easy. So, and I actually forgot one other thing. So at the end here, I forgot that I have the load of By at the other side, which was 25 kilonewtons. And that's very important because at the end of my diagram, it wouldn't equal 0. So we'd have some problems there. So looking at shear, again, we're just going to go left to right. And the first thing that we have at the very left side is 10 kilonewtons upwards. So all that means in my shear diagram, because we start at 0, I'm going to pop up to a value of 10 kilonewtons. So if I have 10 kilonewtons coming upwards, in my shear diagram, I pop up by a factor of 10 kilonewtons. And if I look for the next 2 meters in the beam, nothing happens at all. So if nothing happens at all, then my shear is just going to stay constant and nothing's really going to change in the shear. However, now at x equals 2, we got 15 kilonewtons going downwards. So remember, a concentrated load will just jump our diagram up or down. So we got 15 kilonewtons going downwards. So we're going to go down by 15 kilonewtons. So if we started at 10 and we go down by 15, well, we're going to end up at -5, like this. So this is because of the drop. And then from here to the 1 meter across, we have nothing happening. So we're just going to come across. And then at this point, we see that there's a concentrated moment. And one thing that you guys will have to realize, and this will maybe get some of you, is this concentrated moment, well, it's a moment. It's not going to do anything to the shear. It's just a moment. So our shear is going to have no effect, and it's just going to keep going across the beam like this. So it's going to stay at -5, even past that concentrated moment. However, you guys will realize that that concentrated moment will be very important when we start talking about the bending moment diagram. So for the shear force diagram, well, it doesn't really do too much. However, for the bending moment diagram, it's going to play quite an impact. So as you guys seen, we're now at 4 meters across the beam, and this has been really easy. There hasn't been really anything crazy. We just have 2 straight lines, one at 10, one at -5. So what I'm going to do now is we're going to look at the distributed load. And this distributed load is going to create some problems because it doesn't just jump up our shear diagram. It gradually decreases it or it gradually increases it, but it's not just a jump like the point loads. So what we do for this one is we say that our change in shear, so I'm going to come down here and I'll keep it in dark blue. So I'm going to go a shear diagram. Shear diagram. So our change in shear, which we call delta V, so this is the change in shear between 2 points, is equal to the area of the distributed load. So if we look at this, I know the shear at x equals 4. However, I want to know the shear at x equals 6. So what I'm interested in right now is delta V and then x equals 4 to x equals 6. Well, we know that this is going to be the area of the distributed load between those 2 points. So if we come up here, well, the area here is just going to be that rectangle. So it's going to be the base times height, which is 10 multiplied by 2. So for here, we got 10 multiplied by 2. So this is the area of that distributed load. However, here's one little trick that we're going to have to keep in mind if we're doing this method. It's that 10 kilonewtons is actually going downwards. It's a downwards force. And remember, when we looked at the 15 kilonewton point load that I'm highlighting now, when we had a load going downwards, it causes our diagram to drop down. So when we have 10 kilonewtons of distributed load going downwards, we have to take into account it's going downwards and put a negative sign here. So now we know that our delta V from 4 to 6 is equal to -20 kilonewtons. So when we go down here and we want to find the shear at 6, or I don't know why I did that. So if we're finding the shear at 6, well, we know this is going to be equal to the shear at 4 plus the change in shear from 4 to 6. And basically what this means is, what is the shear that we started at? And if we look up here at x equals 4, we have -5. So we got -5, and then we're adding the change in shear between those 2 points, which we just found is -20. So our shear at the very end of the beam is going to be -25 kilonewtons. So we come down here, and then we can just plot the point, say right here. We can say that this is going to be -25, and we can just, well, actually, this is a good point now. So we now know that the shear at this endpoint over here is negative 25. However, one thing that we're going to have to consider now is how do we get from that point x equals 4 to the new point x equals negative 25? What does the shear diagram do? Is it maybe quadratic like this? Or maybe it's linear like this? Well, this is the next thing we're going to have to pay attention to. And the thing that you guys are going to have to know, and I'm going to write this down too because this is very important, is the slope of the shear force diagram. So shear force diagram, or the slope of the shear, is equal to the distributed load. And I know that this may sound really confusing because if I was taking this in first year, when some professor wrote that down, I'd be like, well, what the hell does that mean? It means this. If I'm looking at this point right here at x equals 4, well, the slope of that point is equal to the value of the distributed load at that point. So I look up here, my distributed load at that same point is 10, or negative 10. And if I were to look at this point at the very end over here at x equals 6, I look up at my distributed load and it has the same value, 10. And if I look at my distributed load throughout x equals 4 to x equals 6, it always has that same value of 10. So what that means is between those 2 points, my shear is actually constant between those 2 points. So if my shear is constant, it must be linear, like this. And it just goes from those 2 points. Oops, I used the wrong color. So it just goes directly from those 2 points in a linear fashion. And, well, that's all fine, but here's kind of the cheat sheet that you guys want to do. So I'm going to write Wx, so this is distributed load. And then I'm going to write shear. And then I'm going to write m of x. And here's kind of things that you need to know. If Wx is 0, so there is no distributed load, then our shear is constant and our moment is linear. And this may be a negative linear or a positive linear. So don't think it's always going up. It could also be the case where it's going down, but it's going to be linear. However, if our distributed load is constant, which it is in this case, well, then our shear is going to be linear. And again, it can go linear up or linear down. And then our moment is going to be quadratic. So, oops, it's going to try an autocorrect. So it can go like this, or it can go like this, or it can go like this, or it can go like this. So lots of different cases if it's quadratic, but what you have to realize is that when we're going from distributed load to shear to moment, it's always one order above. So if this is x, well, then this one's going to be x squared, and then the final one is going to be x cubed. So it's always going to be that one magnitude above. But you guys don't really have to worry about this too much, and I'll talk about this more in the final exam review. So all you guys should know is that if my distributed load is constant, which it is, it's 10 kilonewtons per meter, then my shear is going to be linear. And then at the end of the distributed load here, we have that point load of 25 kilonewtons. And what that does is that brings us back up to x equals 0. So that's kind of another thing too, is at the end of the shear force diagram, you should always be back at x equals 0. Everything must be balanced because it's in equilibrium. So for the shear force diagram, I'm just going to shade it in because we're good to go. So I shade it in to kind of really highlight my negative areas, my positive areas, stuff like this. So I'm just going to do this, and we're good. So that's part B, the shear force diagram, and for all the points on it, we have them labeled 10, -5, -25. We're good to go. But now we have to discuss something else, and it's the bending moment diagram. So I'm going to bring this line down a little bit, give us a little bit of extra room. And I'm going to draw this across. So this right here is now going to be our bending moment diagram. So I'm just going to call it moment at the side. And we know that moment is kilonewton meters. And we're going to start, of course, at 0. Just like this. And we'll do the moment in a different color. So let's do the moment in purple. Yeah, why not purple? So it's the same thing as the shear diagram, where we're just going to go left to right and check for our loads and stuff like this. So starting at the very left, we have no loads, or we have no moments. So our moment is going to start at 0. Oops, zoomed in a bit. We're going to start at 0 right here. But now we got a problem, because if we look all the way up at our free body diagram, well, it doesn't show moments on it, but we know that something's happening in between x equals 0 and x equals 2. So we're going to have to actually come down here and use the same approach that we did for shear, but we're going to do it for moment. So for the moment diagram, we know that the change in moment, so this is the change in moment between 2 points, is equal to the area of the shear force diagram. Well, what exactly does that mean? So if I want to know the moment at x equals 2, so at this point over here, all I have to do is find the total area of shear between those two. So if I'm looking for delta m between x equals 0 to x equals 2, it's going to be the area of the shear. And if I look up, and I'm just going to highlight this, well, that's going to be this area right here, which we see is just a nice rectangle. So our total area between these two is going to be 10 times 2. So we're going to come down here, and we're going to write the moment. It's going to be 10, and it's a positive shear, and then times 2 meters. So this is equal to 20, right here, 20 kilonewton meters. So we come up here, and we know that the moment here is going to be 20. So this point right here, 20. But now it becomes a question that, and the same question we had before, is how does the moment change between x equals 0 and x equals 20? And what's funny is it's actually the same relationship as shear had with distributed load. So in shear, if my distributed load is constant, then my shear is linear. And it's the same thing for moment. I look up here and I see that my shear between these 2 points is constant. So what does that mean? Well, it means that my moment between these 2 points is going to be linear. So the moment diagram between x equals 0 and x equals 2 is going to be something like this. It's going to go linear from 0 all the way up to 20. So not too bad at all. But now we have to look and say, okay, well, what happens between x equals 2 and x equals 3? So now we're going to be looking in this region right here. Well, it's going to be the same thing. The change in shear, so the delta m, or sorry, the change in moment, not shear, from 2 to 3, well, that's just going to be equal to the area under, or the area of the shear force diagram between those 2 points. And we see it's a nice rectangle again, so we're going to have -5, which is the height of it, multiplied by 1 meter. So we're going to have -5 times 1 meter. And this is the most important part right here, is our shear in these 2 places is negative. So when we're doing the calculations, we have to include that -5 right there. So our delta m between those two is -5 kilonewton meters. So we know that from the point x equals 2 to x equals 3, we're going down by 5 kilonewtons. So this is going to be 15. And again, if our shear is linear, constant between these 2 points, which it is, then our moment is going to be linear. So we know it's going to go something like this. So far, not too bad. But now we have something that we can't really predict with our shear force diagram, but rather we have to go to the free body diagram. And that's this thing right here. And it's very important to watch out for these because professors love them. It's these concentrated moments right here. And the reason why professors love them is this, is because they have the same effect as concentrated loads. So as you guys remember, when we have a concentrated load, we jump our diagram. When we have the 10 kilonewtons going upwards, well, our shear force just jumped up by 10 kilonewtons. When we had 15 kilonewtons going downwards, our shear force would drop by 15 kilonewtons. And that kind of makes sense in our head. That one's not too bad. But here's the problem that they have with moments, and this is what gets a lot of students. When we have this moment right here, it's 20 kilonewtons and it's a negative moment. So a lot of students will say, oh, negative moment is going to drop down. However, negative moments, and actually I'm going to write this down so all you guys can see. Negative moments they jump our diagram up. And this is just because of the sign convention that we chose when we cut beams. So I'm going to go jump diagram up. And my little positive moments. They jump our diagram down. So very important. So if we look up here, we have a negative moment of 20 kilonewtons. So a lot of people would drop down. However, we actually have to jump up because, oops, zooming too much now. So we actually jump up by 20 kilonewtons. And we end up here at, actually we'll probably try and keep it as, so we jump up to here. And this right here is what happens. We jump up by 20 kilonewtons. So if we're at 15, well, we're going to jump up to 35, just like this. And this will get a lot of students and I don't blame them, because when I see a negative thing, I assume it goes down. But in this case, a negative thing actually jumps our diagram up. So not too bad. And now we have to look and say, okay, well, we look at our shear. So what happens between x equals 3 and x equals 4? Well, if we look at our shear between these 2 points, it stays nice and constant. So our delta V, or I guess delta M, between 3 and 4, it's just going to be the area under this curve again. So if we look, it's still -5, and the base is 1 meter. So we're going to have -5 times 1 meter. So this is -5 kilonewton meters. So we know that our moment between these 2 points is going to drop by 5 kilonewtons. So it's going to go down to 30. If we're at 35, we're dropping by 5, we go down to 30. And if we look at our shear, it's the same thing. It's nice and constant, so our moment must be linear. If shear is constant, moment must be linear. So now we go to the last part of our thing, or our beam, and that is the change in moment between x equals 4 and x equals 6. So this is the last one that we want, our change in moment from 4 to 6. And remember, this is still all the same. It's just going to be the area under the shear force diagram. So we're going to be looking at this area now right here. So it gets a little bit different because it has a triangular load and as well as a rectangular load. So what I'm going to do is I'm going to go 5 times 2, so that's getting the rectangle out. So this is equal to -5 times 2. And then we're going to do the triangle, so plus 1/2. And the height of this triangle is going to be -20. So the height of the triangle is this distance here, which starts at -5 and goes down to -25. So we know this is going to be -20. So I'm going to have -20 and then multiplied by 2. And when you type all this, it's not really a surprise that you get that our change in moment between these 2 points, is going to be equal to -30. So I'm going to come down here. I'm going to put this is equal to -30 kilonewton meters. And technically, you don't even have to do this calculation because it's the same as shear, where we should always end up at 0. In our shear force diagram, we ended up at 0. In our moment diagram, we end up at 0 as well. Now, this is the only hard part about this question that's going to get a lot of students. And I've marked this question before on finals, and this is usually one of those ones that 50% get right, 50% get wrong. So I'm just convinced that you guys guess at this point, which wouldn't surprise me too much, because when I was in undergrad too doing this, that's what I did. I just guessed. And that is finding out what does our profile look like. So if our shear rate here is linear between these 2 points, well then, as we said, if it's linear, then the moment's going to be in order up, so it's going to be quadratic. And if it's quadratic, well, we have 2 possible scenarios. I'm going to draw them in orange. We got this scenario, so that's quadratic. But then we also have this scenario, which is also quadratic. And this will get a lot of students, and I mean a lot of students. So what we're going to have to look for is the slope at these 2 points, at x equals 4, x equals 6, So it's the same thing for the shear and the distributed load. Remember, I said that the slope at x equals 4, well, that's going to be the distributed load at that point, which was 10. At the point at x equals 6, well, that's going to be the distributed load at that point, which was still 10. That's how I knew it was linear across, is because the slope stayed 10 throughout the whole time. However, when we start looking at the shear now, the value of shear changes between these 2 points. So what I'm going to do is I'm going to look at the point right here, and I see that my shear is -5. So at this point right here on my diagram, I know that my slope is -5. And then at the end of the shear force diagram, at the end point, my shear goes to -25. So my slope at the other point is -25. So it's a lot steeper than it was before. And with this, we can see that our curve needs to look something like this to connect the two. So we come down here and we can put in, oops, go back to purple. We can put in our nice quadratic curve like this. So it must go like this, where the slope gets continuously steeper as the shear goes on. And that's how you figure that out. And I know it's really confusing, so I recommend just maybe looking at it and just look at the shear. We got to find out how the shear is transitioning, and that transition is the slope of this one. So we see it goes from -5, so a pretty nice gradual slope, to -25, which is going to be much steeper in that side. So I hope that was clear. I know it's a little bit confusing, but I hope it helped a little bit. So we look over here. I'm just going to highlight this. I can never really draw this in nicely. So this is our shear, and it's actually positive the whole time, and we have the maximum values, so we're good to go. So this isn't too bad. And if we look at the question, well, we now finished part A, check, part B, check, part C, check. So we're out 8 marks already. So we have 8 marks out of 10. We're good to go. So now we can finish off the question by the last part. It says, and this one will make a lot of people upset, determine the equations for the shear force and the bending moment for the beam. Well, that sounds really bad, because we know that there's going to be a lot of equations depending on which section you guys are looking at. But the question gets a little bit nicer, because it only wants the equations for between points D and B. So basically all we want is the equation that governs this right here, between D and B. Now, when I'm finding equations, and I said this a lot in my lecture, I don't like to actually cut the beam, because remember, we can cut the beam to find them, or we can just do integration. And integration is always the best. Integration is always kind of nice and easy. However, that only works if we're doing kind of quick calculations. And the reason why is because if we were integrating this right here, so this section of the beam, oops, come on, this section of the beam right here, my integral assumes that at point D, x equals 0, which is a problem, because at this question right here, later on it says measured from point A. So what the question would like is for our x to start at A, x equals 0. So this creates a little bit of a problem. We can't use integration, or you can, but you're going to have to use some special fancy stuff. So I don't recommend integration, because integration assumes our x equals 0 is right at the distributed load. However, this question wants us to assume that x equals 0 all the way at point A. So if that's the case, then I find the easiest way is to cut the beam. So remember, we can cut the beam anywhere between these 2 points, and we can get equations using what we know of internal forces. So I'm going to come down here all the way at the bottom. I'm going to put part D, and I'm going to go cut the beam between what was it, D and B? Yeah, points D and B, between DB. So what I'm going to do, every time you cut the beam, unfortunately, you're going to have to draw a free body diagram. So I'm going to draw a beam, or a point. So we're going to have a beam like this. Oh, that one actually worked out surprisingly well. So what I'm going to do is I'm going to draw my internal forces on the, my external forces on the beam. So the 10 kilonewtons, the 15 kilonewtons, those will still all apply. So I'm going to have 10 kilonewtons at this end. I know that there's still going to be the 15 kilonewtons over here. I know that I'm going to have a concentrated moment right here. And this is going to be 20 kilonewton meters. The point load was 15 kilonewtons. and we have a distributed load. But now this distributed load is still going to have a value of 10 kilonewtons per meter, but the distance is going to change. So this is going to be 10 kilonewtons per meter. However, we're not going all the way until the end of the beam because we just cut the beam at this location here. So what we do, because it wants measured from point A and point A is on the other side over here, is we're going to say that this distance from point A all the way to the end of the beam where we cut it is X. So this distance is going to be X, just like that. And what we're going to have to do, since we're now taking loads at a single point, remember, if I said if we're taking loads at a point, well, then we can replace the distributed load with a point load, and we're going to call this one F2. F2. So these were all my external forces that I knew from before. The only difference now is they're at distance X. We have to find out that new distance. However, one thing that we have to worry about now is because since we cut the beam, we now have those internal forces in the beam we have to worry about. So if we cut the beam, we know that we're going to have a shear force coming down, which is going to be V of X. We're going to have a bending moment coming up, which is Mx. And we're going to have a normal force coming across the beam, which is Nx. However, what you guys will see, which is very nice, is it's very rare that we deal with those normal forces Nx because we're only worried about the shear in the moment. So to solve for these, it's actually just simple equilibrium. So if I'm coming through this, the first thing I'm going to need to know is this. I'm going to need to know, okay, well, what is F2? F2, so we know it's just going to be the area of the distributed load, which is going to be 10 kilonewtons. That's the height. But now we got to figure out, oh, okay, what is the length of it? And this is what gets a little bit tricky for people, is trying to figure out this length. So we know that the distance from this end of the beam to the start of the distributed load is 4 meters. Well, everyone knows that. That's not too bad. So therefore, this distance right here must just be 4 minus x. Or sorry, x minus 4. Come on. X minus 4. So when we're figuring out F2 here, the length of it's going to be x minus 4, which is going to be equal to 10x minus 40, just like that. So now what we can do is we can do equilibrium, and we'll go sum of the forces in y is equal to 0. And when we do that, well, we just go right to left, or left to right, sorry. So we got 10 kilonewtons going up. We have 15 kilonewtons going downwards. And then we have F2 also going downwards. So we're going to go minus and then 10x minus 40. And at the very end, we have a V of x going downwards. So minus V of x. And of course, equilibrium, everything's equal to 0. And then from there, our only unknown now is V of x. So when we solve, what we do is we get V of x is equal to, well, I see it minus 10x, so minus 10x. And then I got 10 minus 15, and then plus 40. So what I get is plus 35. So I'm going to come down here, minus 10x plus 35. And this right here is my equation from shear measured from point A. Right there. And now we can do the same thing for the moment as we come down here and we go sum of the moments. And remember, when you cut beams, it's always best to take the sum of the moments about where you cut the beam. So we come down here, well, we look up, well, we have 10 kilonewtons creating a negative moment. So we're going to have negative 10. And the distance between point A and the cut, well, that's x. And then we come across and we got 15 kilonewtons going downwards. So this one's actually going to create a positive moment. And now the distance here is going to be x minus, and then whatever the distance is there, so 2 meters. This is going to be x minus 2. We have the 20 kilonewton meters, which is just the concentrated moment, so minus 20. And now this was where things start to get a little bit messy, because we have F2 creating a positive moment, so we're going to go plus, and we know F2 is equal to 10x minus 40. But the distance from F2 to the cut is actually right here. So it's going to be x minus 4 divided by 2. So x minus 4 divided by 2. And finally, at the end of the beam, which we can't forget about, is we have that mx at the very end of the beam. So we go plus mx, and all this is equal to 0. So if we look here, our only unknown is m of x. So what we're going to do is we're going to solve, and we go therefore m of x after you solve is equal to negative 5x squared plus 35x plus 20. Just like that. So, minus 30. Oops. Minus 30. 35x minus 30. So, this is our m of x. We can put a box around it because this is our final answer. Oops. Something like this. But then we're not done yet, because if we look at the question, it wants us to determine those equations. But at the very end, which a lot of students will miss, because after they find the equations, they go, that was a lot of work, that must be it. But it wants us to find the shear and bending moment at x equals 5 using these equations, which is always very easy, because all you're going to have to do once you have the equations is just sub in the value x equals 5. So when we do that, we get put in v of 5, and what we get is negative 15 kilonewtons. And then we put 5 into the moment equation, and we get 20 kilonewton meters. So now we're done with the question. We can box this because this is our final answer, and we're good to go. And my boxes are somewhat working today. So yeah, now we're good to go. We finished the question. And this right here concludes question 2 of the final. So I'm kind of noticing a trend where this final is quite long. Each one of these questions has been quite long so far. So far, at least in the videos, I've solved questions 2, 3, and 4. And I went over the truss example in class, so you guys are now done the 2016 final. So I hope it helped a lot. My next video, what I'm going to do is kind of a final review, similar to what I did in the midterm, where I'm just going to talk about the final. It'll probably be a 2-hour long video. It'll definitely be a big one, but stay tuned for that. That'll come out hopefully tomorrow, early tomorrow. The Wi-Fi is not really good right now, so it takes a while to upload these videos. So I hope you guys understand, but I promise the worst case scenario, I'll have it to you guys tomorrow. Worst case scenario. So thank you guys all for listening to this video, and I'll see you guys in the next video.